Good morning, everyone. Welcome to Brandforsk and this result webinar. And we are talking today about using sustainable biochar to lower the detrimental effects of fire in concrete. And with me today, I have Oisik Das and Rhoda Afriye-Mensah from Luleå University of Technology. Good morning, Rhoda and Oisik.
Good morning. Good morning.
Good morning, Matthias.
How are you today?
We are doing well, thank you. How are you too?
Yeah, fine, thank you. So tell me, who are you, Rhoda?
Yeah, I am a postdoc in Luleå University of Technology, the Division of Structural and Fire Engineering. And my research area is mostly on material fire safety. So we check how materials burn.
Yeah, oh, that's very good. Very good. And you, Oisik, who are
Hello.
you?
Hi. I am a senior lecturer and also the international coordinator for the department. I do a lot of burning, or make things so that they do not burn. So
Yeah.
But it's fun research on fire and on materials and sustainable structures using polymer and renewable materials as biochar or concrete as well, as we will see today.
Yeah. Yes, actually, welcome back, I can say to you, because you've been here before talking about your research on biochar in other applications. So this is really ongoing area for you. That's very good.
Yes, and I'm quite happy because until 2014, most of the applications of biochar was on soil application and filtration. And then I'm quite proud that I was one of the first person to add biochar to materials.
Oh.
And then since then, during my PhD in Auckland University in New Zealand, and since then we have done a lot of work, and then now we are doing even more high value application. Like we have been able to make graphene directly from waste wood. Rhoda has done a fantastic work on that, which is funded by OFORSH. And yeah, and we have other projects. So it's a lot of fun.
Yeah. Yes, that's very good. Very interesting area, I think, to follow. So it's good work going on. We will see more of you in a while. You're going to present your work here, your project, and we will have questions and discussions with you after presentation. So welcome back in a while.
Thank you.
Thank you.
Thank you. And if you're not familiar with Brandforsk before, I hope you are, but still, this is short information about us. We have a vision, a fire-safe and sustainable society built on knowledge. We develop and communicate knowledge, and knowledge in this case is research, but there are other kinds as well. And this to limit the negative consequences of fire in the society. And we started in 1979, and we are a foundation since 2019. And we have supporting organizations that fund everything that we do. That makes us a collaboration between many parts of the society. And so far this year, we have raised about 7 million Swedish crowns. And we use this money to fund research projects like the one that you will hear about in a while. And also a lot of result communication, for example, this webinar. And you also saw a commercial for our podcast just before we started up this webinar. We also have a research school for practicing fire safety engineers, and we have scholarships for students. And these are our organizations that fund us this year. And so thank you very much, all of you. And if you are not on this list, you are very welcome to become a supporting organization and be on this list too. The program for today, after this short introduction, we will see the presentation from the project. It's about half an hour. And after that, we have time for questions.
So now let's get to the presentation.
Hey, welcome now to the final project seminar, which was generously funded by Brandforsk. And the title of the project is Using Sustainable Biochar to Lower the Detrimental Effect of Fire in Concrete. And the project was done by me as a project leader, along with my colleague, Rodha Mensa. And in this seminar, we will discuss the project results, and hopefully you will enjoy it. So, firstly, concrete. It's one of the most widely used building material in the whole world. It has many benefits. One of the benefits are it's durable, it's quite versatile, it's quite cheap, and it also has low maintenance. So there are a lot of benefits to using concrete, but there are also problems, and these problems are getting bigger and bigger the more we are striving towards sustainable development. So one of the problems is that it has detrimental effect when it is subjected to fire. It loses strength, and it can also spoil. On the other hand, the cement in concrete has very high carbon footprint, and the production of cement has a lot of environmental problems and causes climate change. So these are the two big problems with concrete and cement. So what is the solution can we use? We can use biochar in concrete. So what is biochar? So it's the solid product of pyrolysis. Pyro means fire, lysis is to break. So when you heat any organic material or biomass in absence of oxygen at high temperatures, so more than 350 to 950 degrees centigrade, you get a carbonaceous material called biochar. But why use biochar in concrete? Well, we know that 8% of global emissions, which are caused by humans, comes from the cement industry. That's quite a lot. And in Sweden, where we are, every person produces about 460 kilograms of food waste. So if we can somehow replace cement with biochar, we can reduce these global emissions, the carbon dioxide emissions. And also, if we can convert food waste into biochar, then we are valorizing waste and we're reducing food waste, and it's more efficient waste management. So how are we using biochar in concrete? So we are replacing both cement, as we said that we will, by replacement of cement, we can make it more non-polluting and reduce the carbon footprint. And by replacing aggregate, we can upscale or valorize food waste. So from pyrolysis or of biomass waste, we are making the biochar. But here we are using two types of biochar: a fine biochar, like small particles, and a coarse biochar, bigger particle. The fine biochar is used to replace cement at 10, 15, and 20 weight percent of the cement. And the coarse particles of biochar are used to replace the fine aggregates at the same weight percentage of the fine aggregate. So the idea was to see that if the porous structure of biochar can help water vapor to escape when a concrete is exposed to fire. So when I say porous structure, let's see how biochar actually looks like. So we have, like we said, we have two different types of biochar that we have used in the project. The first is a fine or ground biochar made from wood. And this is on the right hand side, we see the electron microscopy from scanning electron microscopy. The same we see for the coarse biochar, which was made from fruit pit in specifically olive pits. So we see that both the biochar is porous, so it has many pores and holes. And this is where the idea is that, is it possible to, when this biochar is in concrete, can it allow water vapor or moisture to escape when concrete is being heated up? Then also we see the little difference between the two biochars. Like the fruit peat biochar has more compact microstructure, and the wood biochar or the fine biochar is a little more porous. So before we start adding biochar to concrete, we have to understand what are the properties of biochar and how these properties will affect the concrete. The first thing we need to understand is the density. So we have calculated the biochar's true density or the bulk density using an instrument called pycnometer. Usually the density ranges between 1.5 to 2 gram per centimeter cube. And in our case, the fine biochar, which was made from wood, the density was almost 2 gram per centimeter cube. And for the coarse biochar, the density was 1.5 gram per centimeter cube. So we have seen that what the density we have calculated is within the standard range for biochars. Then the particle size distribution, we have used two different methods to determine the particle size, like distribution of this biochar. The first one is laser diffraction method. It measures the angular variation in light intensity as a laser beam passes through dispersed biochar samples. And we have also used a software called ImageJ to analyze the photographic images to find out the particle size distribution. So from laser diffraction method, we use the fine biochar, and we have found out, which is the graph A, that the particle size ranges from 100 micron and then to 400 micron. So the two dominant particle size, one is 100 micron, the other one is 400 micron. And for the coarse biochar, which was made from the olive pit, the particle size was estimated using ImageJ software, and it's about 3 millimeter in size, which was with the figure is given in figure B. Then the water absorption, because when we're adding biochar to concrete, we need water to mix concrete. So we need to understand that when we're adding a new thing in concrete, how much water the new thing will absorb. So we need to find out the water absorption of biochar, and it was done by a tea bag method. It is exactly what it sounds. So we filled up biochar in tea bag, and then we put it in water, and we measured the weight change and at regular time intervals. So what we see from the graph is that the fine biochar, the one made from wood with smaller particle, absorb more water compared to the coarse biochar. And this is because fine particles, the smaller particles, because of the smaller size, the water molecules attach to these small particles, and because of the small particle has more surface area. That's why the water absorption of the fine biochar was higher than the coarse biochar. But what we see that after about 30 minutes of immersion in water, both the biochar has like saturation. Then a very interesting technique. If I ask you, hey, this is a block of concrete or block of wood, can you tell me the mechanical properties? You can easily use instron or 3-point bending test to find out their tensile properties, flexural properties. But biochar is a tiny particle. You cannot put it in instron and stretch it, or put it in a 3-point bending test to find out its flexural properties. We need a new type of instrument to find out the mechanical properties of tiny particle, and that instrument is called nanoindentation. Basically, a known amount of load is given, and an indenter, so it's like a pin that goes down and presses on the biochar particle. Depending on the hardness or softness of the biochar particle, the pin will go deeper and deeper, and that pin will leave an impression mark. So based on the surface area of the impression mark and the load, we can calculate the hardness, and we can get a load and displacement curve that we see on the left. And from the slope of this load displacement curve, we can get the stiffness. So what we have seen here is that both the biochar is more elastic in nature, which means that once you press down, with the known load using an indenter, which looks like a pin, but the tip, its technical term is Berkovich. What happens is that once you load the pin and then you unload, the impression area kind of disappears because it's elastic, but not fully disappears. But this is called elastic response, and this is because biochar has carbon-carbon covalent bonds, which is quite strong. We also see that the fine biochar is more stiff than the coarse biochar, but both of them have similar hardness and both have similar elastic response. But the stiffness or the Young's modulus of the fine biochar is definitely higher, which is around 5 gigapascal, and for the coarse biochar is about 3.3 gigapascal. But the hardness of both the biochar are quite similar at 0.2 gigapascals. Then this is where the fire testing comes. So before we even test the concrete in fire, we have to understand how biochar reacts under fire. So we have used a cone calorimeter. So the principle of cone calorimeter is that almost any material in the whole world, when it burns and when it absorbs, consumes 1 kilogram of oxygen, it releases about 13 megajoule of energy. So every material, after consuming 1 kilogram of oxygen, will release about 13 megajoule of energy. And if we can know or calculate the flow rate of oxygen, we can calculate the energy released. And from that, we can get a host of reaction fire information in cone calorimeter. The similar thing we did for the biochar in our lab in Luleå University of Technology. And we see that, interestingly, the biochar did not ignite and have a very low heat release rate. However, the coarse biochar has a little more heat release compared to the fine one. But the peak heat release rate, which is the highest point in a heat release rate curve, which we see on the left side, it's for both the biochar were very low, like 37 and 27 kilowatt per meter square. If you do it for plastic, for example, polypropylene, it's over 1,000 kilowatt per meter square. The total heat release rate, that is the area under the heat release rate curve, is also quite low. In here, for both the biochar, we see it's about 30 megajoule per milligram. For most plastics, it's like over 100. The time to peak heat release rate is also quite low, and time to ignition, obviously, it did not ignite, so there was no ignition. Now, my colleague will take over, and she will talk about how we added this biochar in concrete, how we tested the concrete, and what are their fire and mechanical properties after biochar was added to concrete. Rhoda, the floor is yours.
Yes, sure. Thank you. So the recipe for the concrete we prepared for this project is shown on this slide. 2 different types of concrete was prepared. The first one is the aggregate replacement concrete, where 10, 15, and 20% of the fine aggregates, which was between the sizes of 0 and 8 millimeters, were replaced with biochar, which had an average size of 2.95 millimeters. And for the cement replacement, 10, 15, and 20% of the cement were replaced with fine biochar, which had a particle size of between 100 and 400 micrometers. So in all, we prepared 7 batches, including the control sample, and about 30 liters of each batch was prepared. After the concrete preparation, we molded them in cubic and cylindrical molds, and they were cured for 28 days, after which we placed them in a humidity chamber that was set to 23 degrees Celsius and 50% relative humidity. So after curing, we did fire test. And in this fire test, we used a fire furnace at the Fire Engineering Protection Lab in LTU. And this particular furnace is, it goes according to the fire curve, the ISO 834 curve, as shown in the figure on the right. And for this experiment, we arranged the samples inside the oven, and we fitted the lid of the oven to prevent any heat losses. And the samples were exposed to 200, 600, and 1,000 degrees Celsius. After that, we allowed it to cool before we carried on with the other tests. After the fire test, we made some observations. At 200 degrees Celsius, no visible changes were seen, but at 600 and at 1,000 degrees Celsius, we noticed significant thermal cracking and color changes. And the thermal cracking could be as a result of the water evaporation, which caused the cement to lose its binding ability. And for the color change, it was due to the iron in the aggregates oxidizing, which changed the color from grayish to brownish. So after the fire test, we performed mechanical and tensile splitting test for both the cubic and the cylindrical samples. And on this slide, we have the results for the cement replacement samples. We saw that reducing the quantity of cement and increasing the biochar content decreased the compressive strength and also made the concrete stiffer. The notable observations we made were that at 200 degrees Celsius, we saw a significant increase in the compressive strength and also the modulus of elasticity. And this was because the heat energy that was provided during the heating accelerated the hydration process, so that increased the compressive strength. And at 600 degrees, we didn't see a significant decrease in the strength, but at 1,000 degrees, there was a drastic decrease, and literally the samples crumbled. It experienced thermal cracking and it crumbled. But if we look at the two figures, we see that with 15% fine biochar in the concrete, the results were not statistically different from the 10% and 0%. And even at 600 degrees Celsius, there's not a significant decrease in the strength. So we can conclude from this slide that even adding up to 15% fine biochar in cement, it can withstand 600 degrees Celsius, which also corresponds to flashover temperature in building fires or structural fires. We also did tensile splitting test for the cement replacement samples in the cylinders, and we noticed a particular trend where the strength decreased with increasing biochar content. And for this particular result, we don't have any results for 1,000 degrees Celsius because the concrete sample, the cylinders crumbled when we tried to do the test, the tensile splitting test. So if you look at the figure on the right, we see that it's just broke into two pieces when we decided to do the test. So we also have results for the aggregate replacement samples. It has a similar trend as the cement replacement samples, but we saw that the overall reduction in strength in the cement replacement samples were more than that of the aggregate replacement sample. In the aggregate, the cement quantity was constant and we didn't reduce it. But in the cement replacements, the cement was reduced, so that reduced the strength significantly. We realized that at 200 degrees Celsius, the strength and modulus increased for the 0 and 10%, but for 15 and 20%, there was a decrease in strength. And at 600 degrees Celsius, the reduction in strength was similar to that of cement replacement. And at 1,000 degrees Celsius, we also saw a drastic decrease in strength. So for the tensile splitting strength, we had similar results as in the cement replacement samples, but we didn't see a significant decrease in strength here. The results are not statistically different from the 0% samples. And also here, all the cylinders experienced thermal cracking at 1,000 degrees Celsius. So we don't have the results for that's recorded. We also did time-dependent fire test. And with this test, we had the intention of exposing the samples to the standard fire curve, that is the ISO 834 curve. And then we wanted to observe the changes in the concrete after 30 minutes, 60, and 90 minutes. For this test, we used the 15% cement replacement samples because the difference in the strength and modulus were similar to that of the 0 and 10%. And after doing the test, we realized that from the graph on the left, we see that the temperature increased up to 715 degrees Celsius. But after the test, we realized that all the samples experienced thermal cracking after 30 minutes. So it was obvious that after 60 or 90 minutes, we would have experienced the same results. So we didn't continue with the rest of the test. So Isaac will take this part.
So after all the test of the concrete, macroscopic test of the concrete, we need to see what is actually going on inside the concrete. And for that, we did microscopy. In particular, we did scanning electron microscopy. Let's look at the microstructure of concrete with biochar. So the first slide, this one, we are looking at three different samples. One is 0%, then the 15% cement replacement and 15% aggregate replacement. We have chosen 15% because, like Rhoda said previously, the 15% biochar added concrete had similar mechanical properties. So we have chosen this sample because this is the highest amount of biochar we can add in concrete and still have the same mechanical properties. So it's the best according to us because the more biochar we can add in concrete, the more sustainable it becomes without losing mechanical properties. That's why we have chosen 15% as our optimum replacement or loading amount of biochar. So if you look at the standard concrete without any biochar, then concrete where the cement was replaced with 15% biochar and where the concrete was replaced with 15% biochar, we see that the morphology looks quite similar of all three samples. In the aggregate replaced sample, we see a big biochar particle as it is pointed out by an arrow, the porous structure, and then we have the cement phase and the biochar particle. It is more visible in the aggregate replaced samples because if you remember, the aggregate replaced samples had biochar were bigger in size, like 3 millimeter. Whereas the cement replaced sample, the particles were very fine, so it kind of mixed with the entire cement phase. So the biochar in aggregate replaced sample were more visible in microscopy. And this is the samples, same samples which were exposed to 200 degrees centigrade. So we see that at 200, no significant changes in the morphology occurs from 0 degree, room temperature, not 0 degree, 23 degrees centigrade. So same, again, for the 50% replacement, we see a biochar particle because the size of the biochar which was used to replace aggregate were way bigger compared to the fine biochar. Now we see what happens to the concrete samples when they were exposed to 600 degrees centigrade. We see few changes. The first change we see is that calcium hydroxide crystals, which were present in lower temperature, are less visible in all three samples. But still, the morphology between the samples, so the standard concrete and the 15% replacement sample and cement replaced sample and aggregate replaced sample, they look, the morphology and the microstructure looks quite similar. And this is where things go a little crazy. This is the samples which were exposed to 1000 degrees centigrade in the standard fire curve ISO 834. So we see a clear change in morphology. We see globules. Basically what happens is the calcium oxide is decomposed, thermally decomposed, it creates calcium salts, which are those globule-like structure. This is from our literature study that we saw that these globule-like structure are basically calcium salts, which form due to the decomposition of calcium oxide. Now, Rhoda will conclude and take it home.
All right. So we made a summary of the fire behavior of biochar concrete and compared it to the standard concrete using the respective temperatures we used in this project. So at 200 degrees Celsius, which represents a small fire, we saw that none of the samples experienced thermal cracking. And at 600 degrees Celsius, which represents flashover fire in structural fires, we saw that all the cement replacement samples for 10, 15, and 20% experienced thermal cracking, but the aggregate replacement and the standard concrete did not experience any cracking. But when we consider the large fire or the fully developed fire at 1,000 degrees Celsius, all the samples experienced thermal cracking. So from this, we can make conclusions that up to 20% aggregates can be replaced with biochar, and we can still have safe structures after fire exposure until 600 degrees Celsius. And also, if we add up to 20% of cement, up to 20% of cement can be replaced with biochar, and we can still have structures, safe structures, until 200 degrees Celsius. So these 2 points are the main conclusions we made from our project. Thank you very much.
So once again, both Rhoda and I, on behalf of Luleå University of Technology, Luleå Tekniska Universitet, we thank Brandfors for funding the project. And what we realize is that biochar does have some benefits. We can replace quite a large amount of aggregate and cement and still have safe structures with aggregate up to 600 degrees centigrade and with cement replacement up to 200 degrees centigrade. So that is good for sustainable development, because the more biochar we add in concrete, the more sustainable it becomes. The more reduction in carbon footprint it gets. But we need to have more deeper understanding of how biochar, like we saw at 1,000 degrees centigrade, all the samples were falling. So we need to have further research to understand the heat transfer in a concrete when there's biochar present. So we need to understand first the thermal conductivity of biochar itself, and how it changes the thermal conductivity of concrete based on the conductivity, density, and specific heat of concrete. So the thermal inertia. So there are a lot of studies to be done in the future, and we hope we will have a good relationship with Brandfors like we have in the past, and continue to make future safe and sustainable. Thank you very much. Thank you, everyone.
Thank you.
Thank you, Rhoda and Oisik, and welcome to the studio. And of course, Oisik, we should have good collaborations in the future as well. That's a very, very interesting presentation. Thank you.
Thank you. Thank you for funding the project. Thanks again.
And now I see we have a third guest here, Dong Wang. Welcome.
Yeah, nice to meet you.
So who are you?
I'm Dong. I'm a new PhD student from OISIC, from China. I'm in Sweden for already 2 months. Yeah, I'm quite new. Yeah, thanks.
Oh, yeah, very welcome. And you are joining Oisik and Rhoda in the research about biochar.
Yes,
it's very good. So we have a question here. It's about the use of biochar and CO2. Nowadays, CO2 is used to cure concrete. If biochar and CO2 both are used in concrete, how do you see the final results on fire resistance Do you have any ideas about that?
I think we need to do tests to understand, because we just use now water curing. So to see, it'll be quite interesting to see how curing with CO2 affects when there's biochar. So yeah, that is something that we need to find out with more research and test.
Yeah. Yeah, thank you. I was wondering, watching this, how do you make this biochar? Is it an expensive process? How will this affect the industry in a greater context?
Thank you for asking that. So, and I've been working on, I always say biochar is like my baby. So we can make biochar from any organic material or biomass. So waste wood, like we have done in the project, from waste food products, bark, landfill, sewage sludge, poultry litter, any organic matter, even plastic waste, tire waste. So, and because it is made from waste, the raw material to make biochar is basically free.
Yeah.
So there we have a price benefit because we're making it from waste. Also, to energy required, if we are giving more energy to get less energy, then we are losing. So, but in biochar, the reaction that creates biochar, which is the polycondensation reaction, it's exothermic in nature. So to make biochar itself, initially we need to give energy, and then we can stop giving energy and it will be self-sustaining itself.
Oh.
So there also we're getting cost benefits because we're not providing energy that much. We're just providing initial energy and we are stopping it. Also, the non-condensable gases such as CO2 and hydrogen and some methane that are produced from pyrolysis process to make biochar, they can be recycled back to run the reactor. Again, then we are saving energy, and energy is money. So we are saving money. So the whole process is not only carbon neutral or maybe carbon negative, but also quite inexpensive.
Right. Oh, that's good. That's good news.
Yes.
Yes. Thank you. You were talking about the water absorption of the biochar. Does that affect the process when mixing the concrete? You normally add water. Do you need more water in your recipe now, or?
Yes, Rhoda can answer that. Rhoda has done the mixing.
Yes, because biochar absorbs water, we have to add more water to the concrete when we are preparing it to make up for the absorbed water by biochar.
Yeah, can I give
Yes.
my answer for that?
Yeah.
Yeah, because the special porous structure of the biochar, so you will absorb the water. And the way to handle this issue is that we pre-wet the biochar before mixing. And then it's actually add more water in the recipe. But this pre-wetting process for the biochar is actually has some benefit for the concrete. Yeah, because concrete, when you cure the concrete, you need water for the hydration. So the biochar with the pre-water, you can help for the hydration, and also for the high performance concrete, because you for the high performance concrete you lose a lot of water, you have some cracks generally. And but if you add the biochar with extra water, you can solve this issue. Yeah. So that's the benefit of biochar. Yeah.
Oh, that's interesting. So it actually benefits in the hardening process of.
Yeah. Sure. Yeah.
Oh,
Yeah.
great.
Thanks. Yeah.
Very good. Here's one. If you imagine a real world application here, will there be any heating effect with biochar added bricks? And will it make a room hotter if you in dry places as it releases heat? Do you have any idea about that?
I don't think biochar-based concrete releases heat. Like releases heat during the hydration process. So, and that is before it is used. So it'll be like just normal concrete.
Right.
There will be no heat release or but the only good thing with biochar concrete or anything with biochar, it can well, it is still under research, but it can shield the building from electromagnetic interference.
Right. Yeah. Another question. You talked about particle sizes. Can you
Sure.
Can you tell us more about that? And you tried some difficult sizes, some different sizes?
Yeah, so basically as we talked in the seminar, that we use two different biochars, and we tried to match the particle size of the biochar with the particle size of the cement, and the particles of the size of the other biochar with the particle size of the aggregate that we have replaced. So the particle size of the biochar that was used to replace cement was 100 to 400 micrometers. And the particle size of the biochar that was used to replace the aggregate, or specifically fine aggregate, was about 3 millimeters. So, yeah.
That's quite large.
Yes, because aggregates are bigger in size, right? So we use bigger biochar particles, and cement are very fine particles. So we use fine biochar to replace cement. So we are matching the thing that we're replacing with particle size.
Yeah, good. Rhoda, you had a very fine slide about your results and your interpretations on that. And is it easier to replace the aggregate than the cement? So do you think you should move on in both directions, or should you choose one and just go for replacing the aggregate, maybe?
I think it is easier to replace aggregates because the cement is very workable with aggregate replacement. But there is an optimal amount of cement that you can replace. And so with that, we can go in both directions. We can choose an optimal amount for cement replacement and for aggregate replacement as well. So it's possible to go both ways.
Oh, good. That's very good. And what do you see next? What's the future in your research now? What will be the next thing that you will do?
Thank you for asking that. So now Dong is the new torch bearer. So basically, like, there's a lot of work done on biochar concrete all over the world. We are also doing that in Luleå. But to be honest, we don't really know what exactly happens to the concrete or the cement when there's a single particle of biochar. Like, we have to, like, if you ask me, hey, Oisik, how does biochar affect polymer? I can give you an exact answer how it affects polymer chemically, physically. Yeah. But with concrete, everyone has speculation. We don't exactly know how it affects. Is it forming crystals in the CS8 gel formation, or is it causing hydration changes, or what is the effect of fire in a fundamental? We don't know that. And we will get some answers as we progress, because Dong is doing his entire PhD on this topic. So Dong will be the pioneer, hopefully, and we will be able to give some more detailed answer of exactly how biochar is affecting concrete in more mechanical way or in fire way, in a more fundamental sense. So we will look deep inside and try to understand.
Oh, that sounds exciting. Do you think that biochar have any binding capacity, or why could it replace cement? Is a question we get here.
Yes, thanks for asking. Oh, it's Conrad. I know him.
Yes, thank you.
No, so biochar does not. So basically, it remains as a solid once we mix it. So basically, it is having a filler effect. And the reason we used to replace cement was more so that the porous structure can allow the water vapor to escape when there is heat in the concrete, and also for sustainable reasons, because if we can replace cement and still have the same mechanical properties as a standard concrete, then we are winning, because in Sweden, about 3,000 kilotons of cement are produced mostly by Cementa AB. And we know that 1 ton of cement produces about 1 ton of carbon dioxide. But if we can replace, like we have 20% of cement with biochar, then we can reduce annually 600 kilotons of CO2. So that's a huge reduction. So it's more of a sustainable impetus, as well as that it can help also in fire. Like we have seen that, you know, if we replace aggregate with biochar, we can still have safe structures even after flashover.
Yeah, that's good. And also aggregate in some parts of the world is something that you lack. We have quite a lot in Sweden, but not in all countries. So
yes,
I guess that's a good course to find ways to decrease that. And we had a question here for Rhoda. Have you tried mixing the waste wood graphene with concrete?
No, we haven't done that yet. It's part of our future work, but I think we expect very interesting results from that as well. So we are yet to see.
But we have added it to plastic, and we have gotten very good fire result with only 2% of that, only 2 weight percent. We have reduced the fire properties by 50%.
Oh, that's very good.
And we are sending that paper to Nature Communications very soon.
Yeah.
As soon as I'm able to read and finalize it, which is a difficult task now. It's a lot of work.
Yeah. So now you added biochar to plastic and to concrete, and what's next?
With plastic, we have quite a lot of understanding already what would have happened. But now we are trying to make more of energy harvesters. I recently sent a Horizon application where we will make a new type of polymer which is inherently fire safe as well as inherently self-healing. And we will use that polymer as a top layer for triboelectric nanogenerators. Basically, it's like a balloon. If you rub your balloon in your head, you have static electricity. Well, not in my head because I have no hair, but you know, people with hair. So it's the same concept. So if we can make a biopolymer which is inherently fire safe, inherently self-healing as a top layer for energy harvesters, and we can use the conducting layer of the energy harvesters with biochar or graphene. So that is our future thing. So if you look at all the Nobel Prizes recently, although they're on fundamental science, but the end application is on energy generation or semiconductor devices. And so, yeah, that is the trend right now. And also concrete is very important. In Sweden, we have a concrete cement crisis going on. So it is extremely important to find sustainable alternatives for cement or reduce the carbon footprint. And we are quite happy that we are able to do that with biochar. And a lot of companies, like big companies like Skanska, they're very interested. And they're already working themselves and with other companies called Biochar Produkter, Potasia, biocoalproduct.se, the audience who are not in Sweden. So a lot of people are working on biochar concrete. But we need to understand more fundamentally how biochar is affecting concrete, and then we can have a better design and recipe.
Oh, that's very good. You're going to be busy for quite a lot of years.
Yes. That is the good thing and a bad thing.
Yeah. No, I think that's good. Do you expect the price of biochar concrete, will it be different from ordinary concrete?
Yes, I think it'll be cheaper. And the most important thing is that all concrete and cement producers can become role model for sustainability. They can get carbon credits if they're using biochar in their products. So there's a huge push towards this thing. And I am in close collaboration with the European Biochar Initiative. That's the biggest consortium of all the biochar companies in the EU region. And I was invited to give a talk in the conference. In fact, I'm going again next week in Italy to give a talk about biochar and its effect on concrete and fire behavior. So yeah, the prices will be less because, like I said before, that biochar can be made from waste, and waste is basically free. So and also you will get carbon credit. So there will be a lot of push from the government and regional bodies to use biochar in concrete. So yeah, there will be cost benefits as well as environmental benefits, as well as mechanical and fire benefits.
Yes,
Yes.
excellent. I'm looking forward to more research done by you. I think it's an excellent work that you've done, and excellent that you really try to find more knowledge about using biochar in our society. That's and it sounds very hopeful. As you say, we save the environment and we also can actually reduce the costs. So sounds very good. Yes, Isaac, anything more that you?
No, thank you very much for funding the project. Thank you very much for organizing this webinar, seminar, and thank you for everything. And thank to my colleague Rhoda and Dong for doing good work. So yeah, they're young people, so they have to carry the torch.
I think that well, thank you all. I think you're doing a great job. Any final words, Rhoda or Dong?
I want to thank everyone for attending and the very interesting questions that have been asked here. And I want to thank Brett first for the funding and Isaac for being a great boss.
Yeah.
Thank you very much.
Okay, so thank you very much. I will just sum things up here and give some information about upcoming webinars to the audience as well. But thank you very much. Very good work, and I look forward to more interesting research from you.
Thank you.
Thanks.
Thank you.
Okay.
So before ending today, short reminder about our fundraising, and you can find more information about that in our webpage. And thank all of you that are funding us, and if you're not, you're of course very, very welcome to do so. And we have a lot of upcoming webinars this fall, and some of them, most of them, are in Swedish, but at least one will be in English. We will talk about fire safety in timber buildings. We will talk about fire as a factor in the life cycle analysis, and also the reuse of fire safety products and inward opening doors for evacuation, and especially when talking about old buildings like old churches and such. And in December, we will have one webinar in English, and that's about limiting fire spread in large floor plans compartments with visible timber. They have been studying a number of setups with timber ceilings that they have treated in different ways. And you can also always find information about this on our webpage. You can also we also have a newsletter. You can sign up for that in the bottom of our webpage, and you can also of course follow us at LinkedIn and other social media. And if you have missed any webinars earlier on, you can see them on the webpage and on the YouTube channel. And we have a podcast in Swedish. This is a podcast for everyone who doesn't like fires, and we speak Swedish in that, but you will not only learn more about fire safety, you will also be fluent in Swedish. And I want to thank my colleagues, Francis and Matthias, working behind the scene with this webinar. Thank you very much. And also thank to our excellent researchers here, and thank you for listening to this, because you're, as an audience and using this as practitioners maybe, or whatever you do, you are important in the chain of implementing knowledge into the society and actually making a difference. So thank you. And again, thank you to all our supporting organizations. Thank you for today. Bye-bye.